the hydrodynamics is biased. This is of relevance, for instance, in food technology. So let's just get started. First of all, I would like to define multiphysics. If you open a textbook, for instance, you would immediately recognize on physics that there is only one physics. But multiphysics, we mean inherently and mutually coupled processes or phenomena. So both must be the case. It must be inherent to the process, it must be significant, and must be mutually. Typically, such multiphysics problems come into categories or flavors, if you like. The first category is a multi-region problem, okay? There you have disparate continua with separate set of governing equations, and these are coupled via interfacial jump and transmission conditions. Typically, jump conditions can be derived using thermodynamics, while transmission conditions are result of conservation considerations. So if you have balance equations, then transmission conditions appear up. So both is important for the coupling here. If you have a second category, this is a multi-field problem, then you have only one single continuum, a subset of governing equations with more than one primary transport or solution variable, okay? So you have the coupling established on a term-by-term basis, for instance, by the source terms. Okay, today's topic will be on a very prototypical multiphysics problem, which is the interfacial heat and mass transfer problem, okay? So we will look into two approaches for conjugate heat and mass transfer problems, two different Dirichlet-Neumann coupling algorithms, if you like. The first one is partitioned. I also say segregated from time to time. The second one is monolithic or coupled. I will come in detail to this in a minute. What are the objectives of today's training session? I want by this training to exemplify crucial building blocks of FOAM's multiphysics capabilities, okay? I want to demonstrate also the relevance of it by disclosing performance differences with respect to convergence. So you will see these two approaches here have very different convergence behaviors. So the accuracy reached will be reached in different times, computational times. I want to provide an executive overview of advanced aspects of interfacial heat and mass transfer, then along two use cases, and one of which you have already seen. This is the surface active agents, surfactant transport, and the other one is reactive mass transfer at evolving fluid interfaces, which complicates the thing, not subject today. And last but not least, I want to substantiate FOAM's matrix support, flexibility, and maturity to deal with these major multiphysics problem classes. So this is the topic of today. But first and foremost, I have to start with some acknowledgements to the community, to all these contributors. First in the list, obviously, must be Professor Herv Jasak and Henrik Rouge from Rica Limited. Then again, Professor Jasak, this time with the head-on as professor of the turbomachinery group in Zagreb. Also Čeko Tukovic, Tessa Urovic, Vuko Vucevic, and Håkon Nilsson, Klaas Jaretek from Chalmers. Ivor Clifford from now at Paul Scherrer Institute, Eric Patterson, Brent Craven, who also gave some valuable training on this topic in former workshops. And I want to thank contributions from my own group, Manuel Falcone, Dirk Gründing, Dennis Hillenbrand, Paul Weber, and Chiara Pesci. The group is run by Professor Dr. Dieter Bote. So after this acknowledgement, I want to give you some references as well. Whenever you come to the need to reference multiphysics capabilities in OpenFOAM, have a look into these references by Professor Jasak and Jemkov Tukovic, for instance, on this topic. Also, there is a recent book chapter on this topic, numerics and multiphysics capabilities of OpenFOAM. And again, I can encourage you to just go through the history of this workshop series and find yourself a training slide set and maybe some material to it about the multiphysics capabilities of OpenFOAM. So this is really dating back to 2010 in Gothenburg. Even earlier sessions can be found where Rouge and Jasak gave some advanced training on implicit solution techniques for coupled multi-field problems. Later on, Brent Craven gave a training on multi-region conjugate heat transfer, which this training is also based on. Ivor Clifford had a very good training on plug-coupled simulation. So you see there's a lot of material out there from this workshop series that you can have a look into. This is the outline of today. And I will start with some introduction to show you the crucial building blocks for multiphysics capabilities. This will have two topics. I will go into detail in domain or say matrix coupling approaches. And I will also cover to some extent equation block coupling to be complete here. Okay, so this gives you already your how to find your way in OpenFOAM in terms of multiphysics. I will also tell you which solvers to look into and give you some code snippets, so you have a clear idea what are the building blocks. Then we will start with some walkthrough conjugate heat foam, which is an own solver version, and you find this own solver version in the public repository of mine under this link. So just go on bitbucket.org, /marshall conjugate heat foam. It's a public repository, so you can just pull it. Okay, here we will look into how the conjugate heat transfer problem at a solid fluid interface is realized in a unified framework. So both approaches, the segregated and the coupled approach, in one solver, and we will just compare partitioned versus monolithic coupling approaches in terms of runtime to reach to a converged solution. Okay. Then we go into the direction of advanced aspects. Here we base our considerations on intertrack foam solver family. This is a moving mesh ALE method. ALE stands for arbitrary Lagrangian Eulerian family. This is basically to treat the multi-phase problem, the evolving interfaces. And on top of this, we build multiphysics in terms of interfacial species transfer and surfactant transport. So this walkthrough will cover heat transfer at an interface coupled via an interface, and this will cover mass transfer coupled across an interface. Okay, and I will end with a task assignment, which means hands-on for you, and the topic will be optimal relaxation and a Git workflow, how you can contribute back into this public repository. Okay. So let's just start into some terminology. We have these two categories of multiphysics problems. One is multi-region, the other one is a multi-field problem category. You also could say here we couple domains and here we will couple equations, okay? We have two approaches, segregated or coupled solvers. And in the segregated, in the multi-region problem category, the segregated solver means we are solving iteratively region by region until convergence, which I would say is explicit coupling. In the coupled solver family, we are solving multiple regions at once, okay? And this is then implicit coupling. On the other hand side, in the multi-field problem, again, segregated solver family, we are solving iteratively one field at a time or one equation at a time, explicit coupling. And in the coupled solver category, we are solving all or say multiple fields at once, which is then implicit coupling. Everything comes with some advantages and disadvantages. Here are the ones I see for coupled and segregated approaches that can be generalized. The coupled approach, well, it has the potential theoretically to handle systems of equations in the most efficient way possible. However, in some cases, it is simply not necessary and also sometimes computationally expensive, sometimes even prohibitive. So one has to carefully check whether implicit coupling is necessary. In the segregated side, the plus is certainly that it is really straightforward to implement. This is what OpenFOAM is made for. However, in some cases, it is simply not working. Either it is also becoming computationally too expensive or too slow or it's diverging if you run into stiff systems, for instance. So these are the pros and cons of coupled versus segregated approaches. So as I said, we will in detail look into a multi-region coupling problem, and you typically read a common terminology. You read about monolithic or partitioned approaches. So here is a definition. Monolithic approaches means basically you cast the governing equations in terms of same variables, and you solve then a single coupled equation system at once. In the partitioned approach, this is different. You have separate governing equations. So this means you basically solve separate matrix equation systems, and you couple them then at the region interface, and you have to sub-iterate, obviously, until convergence in this case. So here's the example. You have two regions, omega 1 and omega 2, with an interface across which the coupling is established by means of interfacial jump and transmission conditions. And these two are the typical solution approaches you're going to have. If you look in OpenFOAM, in FOAMX 10, 4.0, 4.1, for instance, you find a tutorial case conjugate cavity to go into some prototypical example for conjugate heat transfer at a fluid-solid interface. So this is about a steady state conjugate heat transfer to an incompressible laminar fluid. So you see you have these two regions over here, two meshes representing these regions, and the lid is moving here. So you induce some flow into this first region, into the fluid region, and you solve for pressure, velocity, and temperature by the set of Navier-Stokes equations. This is incompressible flow, so this is already divided by density. This is the kinematic pressure. You have the solenoidal condition for the divergence-free velocity field over here, from which you then build the pressure-Poisson equation for pressure-velocity coupling. And here is the energy equation, transport equation, in enthalpy form, resulting in our case in a temperature transport equation. Okay. In the solid, you have the same, but obviously the advection term here is missing. And as I indicated before, at the interface, you're always coming along with the coupling conditions in terms of the jump and the transmission condition. So the jump condition here simply tells you there is no jump of the temperature at the interface. This is also the reason why a bench is not made out of steel. If it stands in the sun, this will get very hot. So there is no chance to find a cool temperature if you sit on a bench of steel. And this is the transmission condition. You have the heat flux coming into the interface, must leave the interface on the other side. So in other words, the interface has no heat storage capacities. Okay, so jump and transmission condition. How to go about it in OpenFOAM? Well, OpenFOAM has a class-based design, as you know, and this allows you to have an hierarchical object registry. So to say, that means multiple named mesh databases. And this allows you to have multiple meshes and fields in one and the same simulation. So one mesh always means one domain with separate fields, separate material properties, separate solution controls, and so on. You have typically one main mesh, so to say, which controls the time advancement. And if you look into the case structure, into conjugate heat cavity, conjugate cavity test case, for instance, you find the main mesh, the main database, by just looking for control dict. Okay, so this is building up some multiple named mesh databases. It is important to note here that every individual mesh represents a single addressing space. Okay, and this has some consequences for the implementation of such conjugate heat transfer type of coupling. Okay, so far so good. I assume you know this kind of case structure already, since you have been using OpenFOAM before. So let's just go on. Now, faced with this conjugate heat problem, heat transfer problem, we have again two options. Just to repeat that, a segregated solution approach, which is explicit coupling region by region, sometimes also referred as loose coupling, illustrated here. So this basically means you solve on one side, you apply, you use the updated boundary condition, apply it to the other side, solve the other side, and so you go back and forth until convergence. The second one is more intense coupling. You have an implicit domain coupling established on a matrix basis. So here's the first one. If you want to look into OpenFOAM, how this is done, just go to heat transfer, CHT, which stands for conjugate heat transfer, multi-region form, which actually is a multi-region combination of heat conduction form and buoyant form, okay? And here, in essence, you run multiple solvers side by side, each on its own mesh with access to its field, material properties, solver controls, and so on. The explicit coupling is done via boundary condition update, as you will see in a minute when I show you the implementation. You have to do one more auxiliary operation, which is data mapping, obviously. So here is the algorithm in a nutshell. You solve the fluid flow and the fluid temperature equation. Then you apply the temperature on the interface, the temperature condition, to the other side, to the solid side. You solve the temperature in the solid domain, and then you update the fluid side by using the fixed gradient data, say the Neumann data on the solid, from the solid side, okay? So this is the algorithm in a nutshell, what is done in OpenFOAM. If you go for the coupled solution approach, this is then about implicit domain matrix coupling. You are facing a general arbitrary matrix to matrix coupling issue, okay? Some variables equations can be coupled, while others may remain separated. In our case, we will obviously solve the fluid flow problem only on one side of the domain, and the solid side here only has the energy transport equation, which you find in both domains. The matrix coupled solvers handle multiple matrices together in an internal solver sweep, combining variables or addressing spaces into implicit coupling. Okay, so what you do here is you solve the fluid flow equations on the fluid side only, and the energy equation now is discretized separately on fluid and solid region, and then solved in a single linear solver call. So this is the difference between segregated and coupled solution approach. And if you want to find an example in foam extent, just go to coupled in solvers and then to conjugate heat foam. So how does this look like? Just to give you an impression, here you build up the coupled FV scalar matrix of size 2 because you want to couple two equations. The first one is the temperature equation for the fluid. Okay, so here you see the direct correlation. You have the DDT term, which is missing over here because you solve a steady state. Then you have the divergence term and the Laplacian term. So just cross out this and you could have the steady state solver. On the other hand side, you're solving for the solid temperature transport equation. You fill them into the coupled FV scalar matrix system and you solve for it. And this is what has been reported already in 2011, a great gain in computational time. So if you plot the maximum relative error over the iterations, you see you have a really speed up of convergence if you compare the segregated solution approach to the matrix coupled solution approach. Okay, and my attempt was now to have this comparison done in one unified solver framework and to make it available for you guys to play around with it and also to look into optimal relaxation. So now this is domain matrix coupling, conjugate heat transfer at a solid fluid boundary. Now let's look to be complete in the multiphysics picture into the other building block that needs to be established in OpenFOAM in order to have a really mature multiphysics support. This is equation or block coupling, okay? So the example in OpenFOAM is a steady state conjugate heat transfer between a porous medium and a fluid flowing through it. And here are the governing equations. So for simplicity, we assume a given, say, a frozen flow field here, and you solve for the temperature transport equation in the fluid. Here you have the advection term, diffusion term, and the source term. And on the solid side, same thing without the advection term. You see the coupling is established via the source terms. You have the solid temperature being held by the temperature transport equation and vice versa for the solid temperature equation. And now if you build up a block-coupled matrix system to simultaneously solve these two equations, you end up with such a matrix structure. Block-coupled means the matrix coefficients are actually replaced, in this case by a 2x2 block entry, okay, on the diagonal of which you see the self-coupling terms, fluid to fluid, solid to solid. And on the off-diagonal side, you see the cross-coupling terms, if you like, solid to fluid and fluid to solid. This is the matrix you build up. You have then the solution vector and the source vector on the right-hand side. How does this look like in OpenFOAM? If you have a segregated solution approach, this is very straightforward. This is what OpenFOAM has been made for. So look at the left side. You see you build up the discretization, the linear equation system, you relax it, and you solve for it, and you do the same for the solid side. So this is the fluid side, solid side. In the block-coupled solution approach, you build up, again, the discretization only. Relax it, solid side, same thing, relax it. Okay, if you want to have a look, go to block-coupled scalar transport form. So this does essentially the same thing, segregated versus block-coupled. Now here, you have to solve still, okay? So what you do next here in the block-coupled side is to prepare the block-coupled system by every block matrix vector 2, because you are coupling two equations, block M, block T, where block T is a wall vector 2 field, okay? You can find it in the create fields. Then you insert the equations into the block matrix system, okay? And you add the off-diagonal coupling terms. Here you add them to the block matrix system. Here you define the scalar field. And then you update the source coupling by removing the explicit sources. And the last one here is that you solve the block coupled system by the solve call. Okay. So now this was for equation or block coupling, just to pinpoint you in a targeted way on the positions in OpenFOAM where to look into to find some examples. Now let's go over to conjugate heat form, which again you can find in the public repository, and on the basis of which I want you to have some hands-on later on after this training. Okay, so again, to have a general overview of what this solver does, I told you it's a unified framework combining partitioned and monolithic approaches. So what it does in the first step is it defines multiple meshes, one per domain or region. Then it creates field variables on each mesh separately. So far, the two approaches are just the same. And then we go into a partitioned algorithm on the left-hand side and the monolithic algorithm on the right-hand side on a user decision basis. If you want to have it partitioned, you just solve the governing equations on each mesh separately, and then you enforce multi-region coupling at region interfaces by coupled boundary conditions. For this, you find in source a patch couple manager class and two boundary conditions which actually make use of this class. And on top level, you then sub-iterate until convergence, typically referred to as Picard iterations. If you choose monolithic as a solution approach, you define the governing equations on each mesh rather than solving it here. You solve it then in multiple matrices. You solve then multiple matrices together in internal solver sweeps. And then as a last step, you retrieve the solutions after simultaneous solutions of this block matrix system. Okay. So to illustrate this to you, let's just walk through it step by step. As I said, the first step is the same for both the solution approaches. We create the mesh. We create the mesh on the fluid side. This will be named fluid, and in C++ code, it's simply the mesh. On the other hand side, we name the mesh solid, and in C++ code, this will be the solid mesh object. Finite volume mesh is defined. Okay, so far, so good. Then we go to create fields. Nothing special here. You have to define your fields to solve for. The only thing that needs to be different if you implement coupled versus segregated is the way you treat the alpha parameter in the equations. If you have a monolithic coupling approach, then you need to actually pick up the boundary conditions, and this is a must read. Okay, so this is why the constructor of the alpha wall scalar field is different if you go monolithic versus partitioned. Okay, so here you see you do not have to read it, but you simply give it the values from the dictionary. Okay, and then you make later on use of simply alpha by saying wall scalar. So this is the difference between these two, and the same is if you go on the solid side for the heat conduction. Okay, so again, for the monolithic solution approach, you have to choose a constructor which picks up the boundary conditions. Later on, the internal field will get some values over here from the dictionary. If you have the coupling method being partitioned, then you do not have to do it. You simply can use the standard zero gradient boundary conditions. Okay, so now you go into the main solver, and here we include t-equations.h. If you have a look, what this is doing, it distinguishes the coupling method again from partitioned versus monolithic. So if you have partitioned, you solve first the thermal energy transport equation in the fluid domain, and then you solve it in the solid domain. And you do this several times according to the non-orthogonal iteration counter. Okay, so here you include the T equation for the fluid side, the T equation for the solid side. You relax, you solve, you relax, you solve. Okay, and the outer iterations take care that you do this until convergence. In this header file, convergence is checked, and it just jumps out until when convergence is reached. So you have kind of a residual control. If you have monolithic, as we have seen in the examples before, what you do is you build up your coupled every scalar matrix, okay, of size 2, because you have 2 equations to couple. And then you add these equations, you fill them in the coupled finite volume scalar matrix system. And then you solve for it, okay? So these are the 2 equations that are used for both monolithic and partitioned approaches. Okay. So here's the outcome. If you compile the solver and you go to coupled solution dict in system folder, you can pick up either partitioned coupling method or the monolithic coupled method. If you choose partitioned, this is the last iteration that is done. And from that, you see, you end up with, say, 2 iterations. When convergence is reached, the execution time is roughly 30 seconds. If you compare this to the monolithic approach, you are much faster, okay? So this is below 5 seconds execution time on my local laptop running in serial. With the same results, this has to be stressed, okay? So now here comes the exercise. Change the meshes, make it make it non-conformal, and try again. Change the relaxation parameter in the partitioned approach and play a bit with these. Can you really influence this drastic difference here? Okay, that would be a first question. Okay, so now to the advanced aspects. If we are running multi-phase simulations with moving mesh approaches, this is typically based on a two-field formulation. Okay, so we have the Navier-Stokes equations present in both domains. And again, we have interfacial jump and transmission conditions in the same way as we have learned it now for the temperature transport equations. But this time we are coupling two domains in terms of the Navier-Stokes equations. So this is done. This is available in FOAM Extend 4.1 under the name Intertrack FOAM. This is the Intertrack FOAM solver family. Okay. What we typically do when deriving these equations is we have a set of assumptions, isothermal conditions. We have two immiscible and Newtonian fluids. So the viscous stress tensor is this one here. We have incompressible flow. We have no slip condition at the interface. What we do typically in research, we allow for additional multiphysics in terms of impurities or species going across the interface. So let me show you how we do it based on what you have learned now. So once more, what is surfactant? What is species transfer? So if you deal with a problem in industry of industrial relevance, you typically find some impurities present in the system in multi-phase flows. And this is nothing but a scalar transport equation in the bulk being coupled to a scalar transport equation on the interface, okay? So you see these species over here. They are called surface active agents or surfactants. They are able to adsorb to the interface and desorb from the interface. Being in adsorbed state, they are subject to advection and diffusion on the interface. And depending on their local concentration, they do change surface tension significantly, so changing the entire flow pattern. Okay, this will be just our first example of a use case to what we have learned. Region-region coupling, but in a non-standard way, we have region coupling of a 3D mesh to a 2D mesh, and we will use finite volume discretization method for the transport in the bulk mesh, and for the interface, we will use finite area discretization. On the other hand side, we have species transfer of multiple species, of a multiple species mixture. So just think of this as a bubble. You have mixtures of different species inside, and some of them cross the interface in terms of interfacial mass transfer. They find themselves in contact with other species in the liquid phase, and they are subject to chemical reactions. So this is reactive species transfer. In terms of governing equations, just let us go through that quickly. So you have a standard equation for both domains, so for omega plus and minus. Remember, you have a two-phase problem. Say this is the gas phase, this is the liquid phase, and in both, you can define the transport equations for this surface active species. On the interface, you have another transport equation, and on the right-hand side of this transport equation, you find a source term, and the source term actually is coupling these two domains. So we have a source term-based coupling. You see what is coming from one side in terms of the diffusive fluxes onto the interface must leave it on the other side, or it is subject to sorption and will appear here as a source term. Okay. Oh, I just recognize I have not mentioned to you the meaning of these brackets over here. So these are jump brackets, okay? They are just telling you the difference of one side minus the other side. What is the difference? And this reads just the difference of velocity is 0 component-wise. Okay, So we have a couple of assumptions and closure to talk about. We typically assume dilute species mixtures. So we apply Fickin law of diffusion, as you can see here. A more general treatment is obviously possible. So you can go to interface Maxwell-Stefan equations. Diffusivity are constant, but very different actually on each fluid phase. And you have a local thermodynamical equilibrium at the interface. And this allows you now to also model the ad and desorptions terms over here. So you have to close for these blue terms here in terms of the transport variables you solve for. So if you talk to experts in the field, physicochemical experts, interfacial science experts, they will tell you you have a kinetically controlled regime and a diffusion controlled regime. Let's call it slow or fast sorption. Slow sorption means the sorption is slow if you compare it to the diffusion process, and the fast sorption regime means the sorption is fast compared to the diffusion. Okay. So in the first case of slow sorption cases, you have even a complicated situation. The source term can be computed as the difference from ad and desorption rates, and you have a fixed gradient Neumann type of boundary condition, which you can compute then from the source term. This turns around if you have diffusion controlled fast sorption. So here the source term must be computed from the Neumann data on the interface, because you have a local equilibrium of the two rates of the adsorption and desorption rate. They locally equilibrate. This, however, gives rise to some Dirichlet fixed value boundary condition over here. Okay, so this you see, you have to build up a very generic framework to actually be able to solve for surfactant transport. And if you have solved all this, you know local concentrations of surface active species on the interface. Knowing this, you can locally compute the surface tension coefficient by means of a surface tension equation of state. And this then goes into the transmission condition for the linear momentum just here. So this is multiphysics simulations because it's mutually coupled. Once more, the boundary condition in the slow sorption case is locally enforced as a flux resulting in Neumann boundary condition, so to say a fixed gradient boundary condition. The source term, however, can be computed directly in the slow sorption case using simply the sorption rates governed by a species sorption model. So here you see we have multiple sorption models being implemented in the typical strategy design pattern. So slow sorption will have, for instance, a slow Henry model, slow Langmuir model, and these sorption rates can be computed just by choosing one of these models. In the fast sorption case, the ad and desorption rates are locally equilibrated. So you run into a stiff problem if you would use the approach of the slow sorption. So you have to exploit the adsorption isotherm. What does it mean? Well, the boundary condition is computed by the adsorption isotherm. This results in a fixed value Dirichlet boundary condition for the bulk equation. And the source term, here you simply use the Neumann data, the flux data. Okay, so you have to choose, because otherwise you run into the stiff problem if you're coupling these equations. And this is how we do it. So you see, on the left column, we solve for the concentration equations of the surfactants on the interface using the finite area discretization. This gives you a finite area matrix entry for the DDT operator. This is the finite area matrix for the divergence operator, and this is for the Laplacian. And then, depending whether you are going for slow model or for fast model, depending on your surfactant system, so to say, you will either add an implicit source or just an explicit source from the model library, from the sorption model library. You solve this system of equations, and then you correct the surface tension according to the local coverage of the interface with surfactant. On the bulk side, not the interface side, you also solve for the surfactant equation, okay? You update the boundary condition accordingly, and then you solve. So this now is obviously, these functions here are depending on whether you have a slow sorption model or fast sorption model being at place. So let me give you two examples. For one is the slow Henry model, the other one the fast Henry model, according to Henry. So here is what is basically done. For the slow sorption model, you have an implicit source term. You can see it over here. So what we do is we basically map C to the boundary, and then we return the source term in terms of the differences of the rates, okay? And for this is now the bulk concentration boundary condition, just updates the boundary, the gradient. Let me just go up again where we are here. You are updating the gradient according to the source term, which is the differences in these local rates, okay? So direct correspondence to the theory. And we build up an entire model library for sorption just being based on this picture. And this now turns around for fast sorption model types, again, exemplified for the Henry type of sorption model. So you see here, the Dirichlet condition is used for the source term. And on the other hand side, we have a fixed value, we use the Neumann data here for the source term. And on the other hand side, we use a fixed value Dirichlet boundary condition, which can be computed like that. And then we are correct for the boundary conditions. So very straightforward once you got the picture, but to do that, actually, you need to recognize that if you would only have one solution coupling method at hand, you would run into stiff problem. Okay, what we can do with such kind of approaches, I want to show you here, just to give you a rough picture of what is possible by using OpenFOAM's multiphysics capabilities. What you see here are three cases of rising bubbles at different levels of contamination. So here you see a low level of contamination, and it is increasing in this series, in this row from left to right, okay? We have used different initial surface coverages for comparison reasons to the experiments. And what you see here is the plot of the rising velocity over the simulation time, over the physical time. And what you see then is, depending on the initial contamination and the contamination of the fluid, you have different behavior in terms of the rising velocity, but the bubbles come then finally to rise at the same velocity. But what you see also is a difference here in terms of the stresses locally at the interface. So these are the so-called Marangoni stresses due to the surface tension differences, due to surface tension gradients on the interface. And you see, in the case where you have almost no contamination, the stresses are located very locally at the rim region around such a bubble surface, while they get more homogeneous if you have higher contamination cases. Okay, let me just give you some impression about this in terms of an animation I have. So where did I place it? Just let me see over here. I hope you can see it. So you see the full dynamics is resolved in such cases by building together and using the OpenFOAM capabilities which were already in place. coming with simple examples, admittedly, but this is what you are able to assemble quickly, relatively quickly, if you really go for it. Okay, let me move back. We have one more example to go, which is also interesting. So let me just move out the window here. And this is species transfer. So do you see the screen? I don't see it.
Yeah, we can see the screen.
Ah, yeah, perfect. Okay. So species transfer again. Let's talk about the governing equations. You already know this guy here. This is the transport equation for the bulk, omega plus and omega minus, meaning on both sides of the interface, you can solve and you want to solve for this species transport equation. Temporal term, advection term, diffusion term, this is the diffusive flux, and a reaction term on the right-hand side where you can use OpenFOAM's ODE solvers. Then we have a jump condition, a transmission condition over here, which tells you, okay, here the interface has no storage capacities for the species. So what comes in from one side in terms of the diffusive flux leaves the other side. And here this is the well-known Henry's law, for the chemical engineers at least. So I'm a chemical engineer, by the way. So this is the concentration of the interface on the plus side is proportional to the concentration on the other side of the interface. And the constant of proportionality is Henry's coefficient, okay? So these are the equations you have to deal with. This is now a classical region-region coupling problem. Now, mass transfer type, while we have gone through a solver for the heat transfer. So you have two bulk equations which are coupled via a transmission condition and a jump condition at the interface. The difference to the temperature case is, the temperature transport case is that Henry coefficient is far away from 1. So you have a jump in the concentrations at the interface. Assumptions, when you derive these equations, just briefly, again, you assume dilute species mixtures. For instance, you apply the Fickin law of diffusion over here. So you have a closed set of equations. Then diffusivities are again constant, but different in each of the fluid phases. And the Henry coefficient is assumed to be constant. This can be changed in a general treatment, obviously. But for now, let's just keep the case simple in that sense, at least. Okay, so our first attempt was then really to go the same way as we do for the heat transport equation and the coupling in a conjugate heat form solver. And what we found out quickly then is, we are running into an instability here. If you plot the concentrations over the iterations, you see you do not reach convergence at all, okay? So the segregated coupling through the boundary condition is working only depending on distinct choices of Dirichlet-Neumann site and data. So if you switch, it might not work anymore. And this was our starting point for research. Again, to remind you, the main algorithmic steps here is to solve the species equation in the region 1. Then we apply a fixed value Dirichlet condition to the interface on site 2, solve the species transport equation in the region 2, and then we update the concentration at the interface on site 1 using the Neumann, using the new species flux that we have just gotten from solution on site 2. So this is our classical Dirichlet-Neumann setup. Now, what is the result? Well, the robustness properties of this Dirichlet-Neumann algorithm really depends on the site and the data to which you apply Dirichlet or Neumann data to. So if we consider a simple 1D diffusion problem in 2 semi-infinite domains, we can do some theory here, and this is what we did indeed. And what we came up with is that the Dirichlet value Gn prescribed at nth iteration can be written out like this, where J is simply the ratio of the two diffusivities. And what the result of this analysis was that the DNA is stable if H square root J, which is again the ratio of diffusivity at the Neumann side and the Dirichlet side, is larger than 2 over pi. So you can come up with some stability regions, okay? So in the first region, you find it unstable. What you have to do is you switch the boundary conditions to stabilize. In the second region, you are unconditionally stable, but the speed of convergence might be improved when switching the boundary conditions. And in the last region 3, you are conditionally stable. So again, switch of the boundary conditions leads to instability. So these are the 3 regions you find, and you can see how they change actually when you go into high or very low Henry coefficients, far away from 1. So how can we now translate this into a stabilization of the DNA algorithm by means of relaxation? This will not be Aitken type of relaxation, which is rather standard, but this type of relaxation will be optimal in a sense, and it ensures non-negativity of concentrations. That was the point of research here. So, and for this, we just looked into the dampening of both Dirichlet and Neumann data and iterating, which leads to this recurrence here. We derive an iteration prescription and look into convergence properties. So this is the spectral radius, which must be smaller than 1. Doing this led us to the optimal relaxation parameter that led to convergence after 2 iterations only. And you see, we only have to change 1 relaxation parameter on one side, while the other one can be left to 1. So how does this look like in terms of implementation? If you go into the source and then into the fixed value temperature equation, you will find such a line for the fixed gradient boundary condition, okay? And here you can simply apply the gradient without any relaxation. On the other hand side, if you go to the fixed value boundary condition for the temperature, it might be advisable to use the relaxation, the optimal relaxation formula that we have just seen. Okay, so you define a scalar field J, you compute J, and then another scalar field for the relaxation parameter, which is this one, and then you'd use a relaxation when defining the equal operator over here, okay? And this then, here I only have pictures, brings you to a solver which can be used in chemical engineering applications to investigate, again, two-phase flows, liquid-liquid flows, liquid-gas flows. Here I'm showing the rising bubble simulation with mass transfer across the bubble interface and chemical reactions. So this is called chemisorption test case. And what you see in the plane here is this product selectivity. This is of high interest to chemical engineers, and the Sherwood number, the local Sherwood number on the fluid interface, which is a kind of dimensionless normalized gradient, okay? So this is the Sherwood number. You can also investigate a kind of enhancement factor, important quantities again for the chemical reaction engineering community. But I think to illustrate you the use of such cases, it's pretty illustrative. Okay. So this brings me now to the end of this training session, and I come at the end to some homework or say some task assignment for you, and I hope to get some feedback from you as well. So the first task would be, please test the formula, I have not yet done it, for optimal relaxation for a conjugate heat transfer problem by just setting the Henry coefficient to 1. And then report, give me a feedback on the possible speed up, the runtime, and the improved convergence rate. And then, if you like, also, we will have a small Git workflow over here. Using Git, please fork the repository. It's openly available, it's publicly available. Fork the repository conjugate heat form that you can find here. pull from your fork remote repository to receive a local copy then locally on your laptop, modify the source accordingly and commit to the Git repository locally again using some descriptive message. Push then to the remote repository and issue a pull request there. Okay, if you have any questions about this Git-based workflow, it's well documented, just go to this link. And if you want to go an extra mile, not only looking into this optimal relaxation, what I currently have with conjugate heat form being published is without actually pressure velocity coupling. So, but this can be easily included by comparison. Please include the Pimple algorithm for pressure velocity coupling on the fluid side and test and submit again via a pull request. So I hope I could show you some of the building blocks of the OpenFOAM multiphysics capabilities that are already there, readily can be used, and how we in our research group use it to build up multiphysics applications in chemical engineering area. And I also hope to hear some feedback from you now with this task assignment. So yeah, and now I'm finished. Thank you for your attention, and the floor is up for discussions and questions.
Thank you very much for the very informative presentation. Yeah, we have a lot of time for the question and answer. If the participants have questions, they can type it on the chat window and I will read it for the presenter. Yeah, the first question is, have you ever tried two fluids, for example, water, air plus heat transport?
So for example, water, air, and heat transfer, yeah, this is something that is actually inherently with the case of species transfer. Yeah, so you can do it by saying the Henry coefficient is 1. Just let me go back to the corresponding jump condition. We have talked about it. Just this guy here. So here you see there is no constant of proportionality other than being a 1 here. And for the species concentration, you have this, where is it, this Henry coefficient. So just saying this is 1 will get you to the same equations for also gas-liquid flow. So yes, it's possible in this framework.
Yeah, thank you. The next question is, very nice presentation. Do you also have experience with simulations with a movement of the interface?
Yeah, I mean, this ALE interface tracking framework is a moving mesh method. So basically, the interface is approximated by a part of the mesh boundary. And as the interface is fluid and evolving with time, you need to move the mesh accordingly, okay? So this is moving the interface around. Yeah. Also, I have to tell you this, where is it? This guy here is no classical temporal derivative. It's a so-called Thomas derivative. It's the temporal derivative following the path of the interface. So yes, this is indeed the core of expertise here.
Yeah, thank you. The next question is the number of coupled equations for coupled block solvers limited?
By no means, no. I mean, it will be steered by the tolerance you set in FV solution. Okay.
Yeah. The next question is, you were talking about the coupled solver, which is available in foam extent. Is there a chance to see this improvement in the ESI OpenFOAM Plus version?
The answer is yes. We have been discussing it last year. Now Corona crisis happened, so I think the things will slow down a bit. But we are many technical committees in the ESI governing structure have requested such kind of functionality in the ESI version, and I think it's the next step to go. It's really a pressing one. That's my impression. Yeah.
Okay. The next question is, so for example, if I send CO2 gas through pipe holding liquid MEA, will it show absorption of CO2 gas based upon your Hemi absorption?
That's not a very detailed one. Can you repeat it?
Yeah.
Just give me a
If
second.
I send CO2 gas through pipe holding liquid MEA, will it show absorption of CO2 gas based upon your hemi absorption? Does the solver work with ISO advector numerics? That's the second question.
Okay. Last question is more easier to be answered. No, it does not work with the ISO vector because this is a kind of VOF-based solver. What we have been talking here is not interface capturing volume of fluid method, but interface tracking arbitrary Lagrangian Eulerian method. So a complete different solver family, if you like, also approach family. One can think about it. It might be more useful to make it work with GIB functionality of Angus, for instance. So there you can gain more flexibility. Regarding the questions of absorption, we have done also volume of fluid work. You find it actually in the same repository together with Linde, so you can use it for the absorption simulations. There's a solver for it separately, but that would be another talk, another training.
Yeah. The next question is, can the solver handle radiation heat transfer across region boundaries?
Yes. So we have, I just commented it out in this presentation because the code snippet became too long, but it is added to Form Extend 4.1, so radiation is there.
Okay. Can such models handle the reduction of volume of the gas bubble when the species transfer occurs from the gas to liquid?
Very good question. We have implemented a phase change implementation. We have implemented such a mass transfer term, changing the volume. This will also influence we will have an additional term in the discretized space conservation law. Then you have to add this term in the fixed value boundary condition of the velocity and into the pressure a boundary condition. Then you will see the bubble shrinking due to phase change, either due to thermal phase change or due to volume effects due to mass transfer. It's perfectly possible. We have not done a lot of research in that direction. So if you have some application in mind, please contact me. Yeah.
Yeah. Next question is, have you tried to use quasi-Newton acceleration instead of under relaxation for the segregated approach? For the FSA problems, we typically observe a speed up of 3 to 5.
Perfect question. No, we have not yet tried it. Please go ahead. I mean, this task assignment I gave is not only restricted to the optimal relaxation factor I have presented. If you have some idea in mind, the framework is there. Please let me know and we can have a discussion.
Okay, the next one is, would these kind of models work for droplets instead of bubbles?
Yes. Short answer, yes. It will work. The only thing you have to take care about is that depending on the differences in viscosity and first and foremost density, you might run as well into instability issues. But nowadays, Ceko Tukovic, who is the original author of the ALE interface tracking framework in Form Extend, did also an implicit coupling implementation of the interface tracking solver family. So if you run into problems here, contact him. I'm sure he can be of help.
I think this is again the follow-up. I would like to specify my question about the number of coupled equation. I have seen the template parameters vector 2, vector 4 when defining the coupled matrix. This leads me to think that there might be no vector 10.
Well, you have to compile it. You have to do it yourself then. Yeah, so it comes with a set of pre-compiled options. If you have other numbers, then you have to compile it once more and then you can use it. Yeah.
Next one is, can we use this solver to capture moisture from moist air when it flows through a porous media like a sponge?
Solver to capture moisture from moist air when it flows through a porous media. This is another type of question. We need to talk about how the capturing happens. There we need to talk about physics, what actually happens when the moisture is captured. I cannot answer, so maybe contact me and we can discuss.
Okay. The next one is like, how does the block coupled linear solver know what cells are to be coupled in a multi-region monolithic case? Does the interface need to be declared separately?
Very good question. I think I were too quick here. So what you have in the block coupling, let me just see, this was partition monolithic, is I need to go to create fields over here. Okay, typically you will define the fields where you couple it in the boundary condition part of the field files, okay, in the zero directory. And here I just pointed you to the place where this makes a difference in the code implementation. So you have to define it on a case-by-case basis. And this is using basically attach detach functionality. This is a boundary mesh modifier, which simply takes a set of, say, internal faces and makes them boundary faces and vice versa. Okay, so this is how the monolithic coupling happens, but you need to tell the solver which boundaries you want to couple and which not. Okay, so just have a look into the conjugate heat form solver, and there you see detach and attach as a members, and then look it up downstream the code what happens.
This is about the sharing of the slides in the video. Are you going to share your slides on OpenFOAM 15 website, and would it be possible to have a recording of the talk too? And,
we did not record the talk, but the slides I will obviously deliver, so you will find it on the website of the workshop. Yes.
Okay. Yeah.
So now there's
yeah, you can continue.
Now there is some time even left, I think, for you to really take the time, download the repository and try to have a few tries on this conjugate heat form solver. Can you influence the convergence rate? Compare the numbers, are they the same as for my run here, over here? And can you contribute to the public repository in sense of the optimal relaxation I have just been presented?
Yeah, for your information, again, this is being recorded. So if you're agree to share the video, then we can put it on the website, and that's what they're asking to. Yes.
So I would rather like to leave it with the slides, if you don't mind. I think they are very comprehensive already. Obviously I'm available for discussions. So if you have any questions regarding the content of the slides or your findings, please contact me.
Okay, sure. And yeah, that's all we have. We can, if you have more questions, you can type it on the chat window. Can you share the link to Bitbucket again?
Yeah, sorry. I think it was all the way up here. Here you go. So it's bitbucket.org, then H Marshall, which is my name, my repository, and then conjugate heat form.
Yeah, this is from the moderator. This recording is for the organization purposes. Presenter would have to agree in order to them to be shared. He's going to share the slides to the organizer, who will then share it to the website for participants at a later time.
Thank you.
Yeah,
Dr. Holger, you'll have the recording on your computer once we stop, since I made you an actual co-host. Therefore, it will be for your own purposes, and we will not share these without your behalf.
Okay.
Yeah, there is one more question. Have you come across your solver with the periodic boundary conditions, such as cyclic AMI?
I have come across it, obviously, but not using it here for the multiphysics functionality. Yeah.
If you have more questions, you can type it on, and we have time till 10. think maybe that's all we have.
I think they are all now hands-on with the tutorial. As I said, I can just encourage you to go through the steps of the task assignment, so to learn the Git workflow a bit, and to get into discussion with me about the multiphysics capabilities. And hopefully we have a fruitful discussion in the upcoming week. So thank you.
Yeah, thank you. Let's thank the speaker again for the wonderful presentation. And thank you everyone for joining the the session. And next session will be around at 10:15. Hope you all join there.
Thank you all. Have a good day.
Bye-bye.